The last talk is RaceInjector, injecting races to evaluate and learn dynamic race detection algorithms. Michael's presenting. Oh, Michael Wang will be presenting.
Okay, so everything's set up. Michael, try to speak. But we don't hear you.
Okay, am I?
So we see your slides, but...
Okay, can you hear me okay?
Yes, so you can go ahead.
Sounds good, thank you. Okay, hi everyone. I can't actually see any of you, but hopefully you're having fun. So yeah, this is a work called the RaceInjector. It's for evaluating dynamic race detection algorithms. Some work that we did at MIT with my great collaborators, Shashank, Malavika, and Unime. So, yeah, just an outline of this talk. So first, just going to talk generally about the problem, some current methods of how we detect race conditions now, so kind of the state of the art, and talk about how we envision RaceInjector kind of fitting into the picture. So there's a lot more concurrent software these days. It's probably not a surprise to anyone. And an issue with concurrent software is that these multi-threaded programs are difficult to write correctly. There's bugs like data races and deadlocks, and particularly, they can be very hard to reproduce since they're often dependent on the specific interleaving. So they're non-deterministic, meaning that during testing time, it's hard to manifest these bugs sometimes. And they can be very expensive to fix. So this talk will be focused specifically on data races. And just a brief refresher, data race happens when two threads try and simultaneously access the same shared resource. So the application that I usually like to think of is, let's say you have a ticket buying application for an airplane. A data race would occur if two different passengers were able to simultaneously book the same seat, which is something you don't want to happen, obviously. And the typical way to test for this is through dynamic testing, or a very common way, I should say, where you take the program, in this case, let's say it's our ticket application, you execute it, and during each execution, you record a log of all the events. And each of these logs we'll refer to as an execution trace. And we pass each execution trace through an analyzer, which will determine if there's a bug or no bug. So to be a little bit more concrete on what this would look like with a data race, here we have two traces. On the left, the important events are these events in the red, which are two writes to a shared variable. And so here on the left is what we call a potential data race, where there's two writes, and they're unsynchronized, meaning that they can execute concurrently, but that doesn't manifest in this particular execution. On the right side is another execution of the same program, where they do actually execute concurrently. So here you can see that the two write events are adjacent. So on the right here, this is what we call an observed data race. And on the left is what we refer to as a potential data race. Finding an observed data race is trivial. You basically just see if there's any simultaneous accesses. But what we want, and what's a lot harder, is to detect if there's a potential data race. And that's what we're going to be focusing on. So a very common solution is approximating an ordering of a program. And what an ordering does is it takes a single execution trace and tries to create an order in which the events have to occur. So what that means, if two events in the trace are ordered, they cannot execute concurrently or simultaneously. And if two events are not ordered, they can execute simultaneously. So what this means is we can take a trace, we can generate an ordering, and if there are any two conflicting axes that are not ordered, it's a data race. So to be a little bit more concrete about this, here's a ordering algorithm. It's called happens before. It's kind of the first one. And what it does is it draws an ordering between thread events. So in this trace here, we have two threads. And an arrow kind of represents the ordering. So we have an arrow between all the events within a thread. And it also draws an ordering between any critical regions. So here, there's a critical region which acquires a lock. In the second thread, there's another critical region on the same lock object. So there's an ordering between the two critical regions. And here, there's two writes to the same variable, and these writes are not ordered. In other words, you can kind of think of it as there's no path from one write to the other. So this is a race condition that is detected by happens before. There are two axes to the same object that are not ordered. So happens before is great, of course, but it's incomplete, meaning that it can miss races. It's sound, meaning that it'll never give any false positives, but here's an example where there's a race condition and critical regions in between, and happens before will not be able to detect this race. So there's definitely some rooms for improvement. And there's been a lot of work in the past, 10, 15 years, which are improvements on happens before. And one thing to note is these typically are all sound, meaning they don't have false positives, but they're incomplete, meaning they might miss some races. Another method of solution that I want to touch on briefly are SMT-based solutions. So what these do is they frame the race detection problem as an SMT formula and try and use solvers to determine if there's any alternate executions that can be racy. So I'm going to go into a lot more detail on these later in the talk. Right now, I kind of just want to mention them and kind of plant the seed. And one thing I want to also mention is that these are complete, meaning that they're guaranteed to catch all races, or typically are guaranteed to catch all races, but they're very expensive. When you have a trace that can be millions of events long, it's not feasible to run a solver on the entire trace all at once. So typically, what these algorithms will do is they'll run it on just a subset of the trace. Most common is around 10,000 events, and what this means is it'll catch races that are 10,000 events, within 10,000 events, but if there's any race condition that's more than 10,000 events apart, meaning that there's more than 10,000 events in between the conflicting axes, it won't be able to find them, or you won't be able to find them with one of these SMT solvers. So kind of the question that motivated this work is, how do we actually measure improvement within these algorithms? So here's a snippet of a table from a race detection algorithm called WCP. It's from 2017. It's a partial ordering algorithm. And it compares itself to happens before. And what you'll see in these two columns that are highlighted in red is these are the number of races that are detected by these algorithms in each of these programs. So WCP detects 4 race conditions in account, 4 in airline, etc. And the way that they show improvement is that they prove that WCP catches a superset of all the races that happens before detects. So every race that happens before is able to detect is also detectable with WCP. And WCP is able to detect additional races. So you'll see in Eclipse, it's able to detect 2 more races, and Jigsaw, it finds 3 more races than happens before. And this is a great way of evaluating. It obviously shows improvement over the years. But one question that we can't easily answer through this type of evaluation is how many race conditions are being missed by these algorithms. Where, let's say, tool 1 is happens before, and tool 2 is WCP. We know that it does better and that it's a superset, but we don't have a good way of approximating this red region, which is all existing races. We don't know if happens before is, detecting 99% and WCP is detecting 99.1, or if happens before is only detecting, 2% of races. And this is a question that's very useful where you want to know or have some sense of, if I run one of these algorithms on my program, how safe am I from race conditions? And that's still a very hard question to answer. Ideally, the way that you would address this is with a dataset, which is typically what they'll do in machine learning applications, where you'll have a dataset of labeled samples. So in this case, what that would probably look like is a dataset of programs or traces with ground truth labels for exactly where there's a race condition and where there isn't. And what we would like to do is be able to run one of these algorithms on that dataset, and we'll be able to see how many of these race conditions are caught and how many are missed, how many true positives, etc. But it's really hard to generate this dataset in this field. Finding a race condition in the first place is really hard, and it's a bit of a catch-22 problem where if we're able to scalably find race conditions to generate a dataset to see how well we can find race conditions. So there's been some prior work on this. Typically what they'll do is they'll look at open source software and look through commit messages to see any fixes that are race conditions. And these are really good data sets, but they're typically pretty small just because it's hard to find a lot. And it's hard to it's hard to use that to motivate a lot of future work with such a small sample size. So this work is to address that, and what we try and do is we try and use an SMT solver to create this data set. Typically, these solvers that I mentioned earlier, what they do is they'll take a execution trace and determine if there's a race condition. What we're going to do is we're going to use the solver to instead introduce a race condition and use those introduced race conditions to evaluate existing tools. And this solver is what we call RaceInjector. So for the rest of the talk, I'm going to talk about how RaceInjector works and any future work around it. So there's 3 steps. The first is to collect a trace of an existing program, and we call this a base trace. Next, we add a trivial or observed race into the base trace, and then we use a solver to convert that trivial or observed race into a potential or more interesting race condition. So the first step is to collect the base trace. So this is very simple. You just take a program, execute it, and collect all the events. So nothing special here. It's probably been going on since before I was born. And the second is adding an observed race condition. So what's important here is we don't want to modify the trace too much, and we don't want to change. We don't want to violate the initial semantics of the program. So what we do is we look for any areas where there's a context switch, so where the execution flows from one thread to another, in this case from thread 2 to thread 1. And we introduce 2 write events to a new variable that isn't seen anywhere else in the program, or a new memory location. And so because it's new, it's not going to change the semantics or violate the semantics of the original program. So finally, we want to turn this observed race into a potential race. So here I'm going to take a small step back and talk a little bit about how solvers work to detect race conditions. And the general formulation of the problem is, given a trace sigma, is there a valid reordering sigma star such that there exists a manifested or observed race condition? So given this trace on the left, is there a valid reordering where a race condition manifests? And I'll get into what it means to be a valid reordering a little bit later. In other words, the question could also be framed as, is there a valid reordering such that 2 conflicting accesses to the same variable are adjacent? So what we're going to do is we're going to try and reframe this or reverse this such that can we discover a valid reordering such that the two conflicting axes are far apart? So I want to talk a little bit about what it means to be a valid reordering here. So the first constraint is that the intra-thread events stay in the same order. So we're assuming a sequential memory model here, where on the left we have a trace, and the right is an example of an invalid ordering. And here it's an invalid ordering because the write event and this release event are in a different order. The second is that critical regions can't overlap. So here we have thread 2 acquiring and releasing a lock, and another thread can't just acquire the lock while another thread holds it. So pretty basic locking semantics here. And finally, the read-write consistency has to be maintained. And what that means is for any read event, the immediate preceding write event to that variable has to stay the same. So here the read event on line 6 reads from the write event on line 3 or event 3. And in this reordering, you can see that the write event comes after the read event. So this would be another invalid reordering for the third reason. And the reason that this has to be maintained is just so that control flow is maintained. Since you don't know that the events after this read event might be dependent on the value that's being read. So we want to make sure that all the values that are read stay the same. So a valid reordering to detect potential race conditions must maintain the three prior conditions I just mentioned, and the distance between conflicting axes is 0. So in this case, there's two conflicting axes far apart. In the second one, it's 0, since they're right adjacent to each other. And it's probably pretty clear by now, but what we want to do is have the distance between the conflicting axes be greater than some constant. And so basically we want at least n events between our two conflicting axes. And one problem that's important to keep in mind here is that I initially mentioned that the computational cost of these solvers is pretty high, which is kind of the blocking point. And so we need to address this somehow, since one thing we want to avoid is introducing a race that's trivially detectable with a solver. And our insight here is that the solver cost, the cost of running a solver, is exponential on the input length. And what that implies is that it's much more efficient to run the solver multiple times on smaller inputs than it is to run it once on a very large input. So that's what we do here. So here's an example of a trace where let's take these two red events as the events we want to move apart. And let's say the whole trace is too big to run our entire solver in one shot. So what we do is we just run our solver on one segment of the trace. That moves the events apart a little bit. Then we run it on another subset where we move one of the events forwards. So we move it forwards, repeat until we can't move it forwards anymore. And then we do the same thing with the other event, but we move it backwards. And we end up with a trace that has our racy events very far apart, which is much more efficient than moving it all at once or running the solver on the entire trace all at once. And it's pretty cool that that just a chunk being validly reordered and reinserted still maintains the integrity of the whole trace. So I'm going to talk a bit about our results. So we evaluated RaceInjector on five different programs, so ArrayList, TreeSet, Jigsaw, Stack, and Linked List. And we tested 4 algorithms that have come out since Happens before. So for each of these traces, for each of these programs, we just generated a single trace and then ran RaceInjector on each of these traces. And here a check mark means that we are successfully able to insert a race condition that is undetected by the algorithm. So here, a check mark on array list means we're able to insert a race condition into array list that is undetected by happens before. And this is pretty important because we want to make sure that the races we inject aren't just super trivial. Since what we want to do is we want to motivate future work, and if they're all super easy to detect, there's not much to take away from it. And so we're able to inject races into all of these, into these 3 traces that bypass the existing algorithms. So right now, we only generated about 4,000 traces, I believe, and so it's not quite enough to say anything conclusive. We just don't have enough data yet, but it's pretty cool that it shows that there definitely is some room for improvement and some races that could be going undetected by these algorithms. So one problem that comes up with any synthetic bug work, or I guess any synthetic work in general, is how realistic are these synthetic bugs? There's been some work in other fields. This particular paper is on vulnerability detection, so injecting vulnerabilities into programs. And they've found that synthetic bugs aren't necessarily representative of real bugs. So this is definitely something we want to keep in mind. And in particular, for a RaceInjector, we introduce a new variable specifically for the purpose of having a race condition, which, I mean, I don't do that in practice, and I'm hoping that no one else does, but guessing that there's some work that needs to be done there and making sure these bugs are realistic. But a big question is, how do we actually evaluate the realism of these bugs? So as we're kind of iterating on RaceInjector, when will we know when the bugs are actually realistic? So what we want to discover is the overlap between these RaceInjector bugs and these real bugs. And kind of our proposed experiment that we plan on doing here is to see if a machine learning model trained on RaceInjector bugs can predict a small curated data set of real bugs. And so kind of our pipeline here will be, we'll take a machine learning model, train it using RaceInjector bugs. It'll output whether or not there's a race and where the race is. And then test it using real bugs. And because we're only using these real bugs to test the model and not train it, we don't need a lot of data. Just 100 or so, or a couple hundred will be sufficient there. So if it is, it'll imply that the distribution of RaceInjector bugs is close enough to the distribution of real bugs such that we can train a machine learning model, and it implies that our bugs are at least semi-realistic there. So just as a conclusion, we're able to inject and generate races inside of traces, some of which are missed by state-of-the-art algorithms. And we hope that a data set of these bugs can motivate the development of more algorithms or potentially use learning-based approaches for the problem. But that's it. Thanks so much for sticking around. Hopefully you're not too bored and tired by now, and happy to take any questions.
Okay, thank you. So first of all, there is a comment in Discord by Tucker Taft that, I agree in the sense that he says the use of sound versus complete in the race detection literature is exactly the dual of what we do in static analysis community, okay? And it's a really annoying problem that is not only about the race detection literature, but it's a common problem of what is soundness and what is completeness. But I think everybody is...
Oh, really? Wow.
Yeah, just check the comment in Discord and... Yeah, but that's perfectly fine. I think we are used to these kind of things that happens quite often. Now, I have a question because I really found very interesting your approach, and I wanted to hear from you if you have already thought how you could generalize your approach, I would say, in two main directions. One is, do you think you could extend it to other properties? I don't know, null pointer exceptions, things like that have nothing to do with data races, but where we still need to have benchmarks in general, because today there was a talk, I don't remember which one, but one that was using the Juliet test suite. Okay, so that kind of test suite or the OWASP benchmark for web vulnerabilities are really, handmade, and they always repeat the same pattern forever. So first question from my side is, do you think this could generalize to other properties that maybe are already treated by SMT solvers, okay? But of course they have nothing to do with data races.
Yeah, I'm not familiar enough with how those solvers on other domains work. So it's hard for me to give, I don't think I can give like a super informed answer, but I suspect there's definitely some work. There's a lot of work in, introducing buffer overflows that have been pretty commonly used. But I suspect that that the same high-level approach could be applied. But I'm not familiar enough with the specific constraints for those problems to really say.
Okay, and then the second question from my side was more about instead of starting from a safe program, try to build up a wrong program. What about starting from a safe program, adding some noise, but the program is still safe, but trying to have the static analyzer confused and produce a false alarm?
Yeah, no, that would definitely be interesting as well. So basically, kind of measuring the opposite problem, measuring how many false positives there are. Yeah, so I think there has been some work on this. And a lot of it, from my understanding, is kind of an adversarial machine learning approach, where basically they try and modify an existing program to fool a detector. I think it's been done on some I'm not sure the specific domains or all of the domains it's been applied, but they've done work on fooling code summarization models, where just by changing one variable, the model predicts something completely wrong. I'm not aware of any work that's been done in that sense on other tasks, but I feel like obfuscation is for a lot of that purpose. I don't know if it's specifically targeting a specific task, but
well, for instance, if you give a look to the Juliet test suite or the WASP benchmark, they are doing some kind of manual obfuscation. I would say they just add random noise around to confuse the static analyzer. So yeah, you're right. I don't know. Maybe it's an interesting direction. Any question from the audience? Yeah.
Thanks. Yeah, nice talk. So I was wondering what other languages you plan to support in the future. And I didn't see any mention of language here, so just...
Yeah, sorry. Yeah, no, good point. Sorry. These are all on Java. All these programs are Java programs. Typically because that's what the algorithms have been targeting, but the approach, I think, should be agnostic to any language. So probably the first iteration, we're on Java, but I definitely would be really interested in extending it to other languages, so we can maybe target like browsers or something.
Okay, got it. And the second question is, how are you sure about like that 100% number? Because
sorry, the first
you mentioned like the motivation of building RaceInjector is to determine all the unknown data races, right? Yeah. So what is the baseline? Because you don't have any ground truth. So how are you comparing that you are missing X percentage with your approach? So what we're trying to do is generate races that we have ground truth for to approximate this. So we're not doing any detection ourselves, we're just generating the races. And the tools we're evaluating are the existing tools. So the main issue is that there's no data set of labeled races, meaning that there's no existing set of execution traces where we know there exists a race condition. And so that's what we try and generate with the race detector. And so, sorry, let me scroll back to the chart here.
And so what this means is we generated 4,000 total races and happens before missed 60 of them. I don't know if that answers your question.
Yep. Okay, any other question from the audience? Otherwise, let's thank the speaker again.